Alright, welcome back. This is a Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing mathematical modeling. This is Chapter 2, Discrete Time Models. Section 2.2 is going to be solving first-order difference equations. Primarily, we're going to give a systematic method for solving linear first-order difference equations. Solving nonlinear ones in general, whether they're first-order or higher, it just gets worse and worse, but these are non-trivial tasks. But we will discuss them in this course as we go. But we're going to focus on first order primarily, and in that scenario, this lecture specifically will solve first order with in mind making the clear distinction between linear and nonlinear. This one we can do systematically and have a discussion and a solution for them. These ones are non-trivial and nonlinear. Let's get to it. A first order difference equation is essentially going to be a rule that relates the quantity xt at time t to only the previous timestamp t minus 1 and time t. The most general form, therefore, and in most books where they're going to start, and this is where also, if you look at the previous video, in one of the end remarks, you'll see why you lose, why we call these difference equations, but you don't see a difference anywhere in these. But we can move the difference, the xt minus 1, to the other side and absorb it into this function, and then everything will be okay. But the most general form of this either going to be xt is a function of just the previous guy and time, or xt is going to be just a function of the previous value. In this scenario we call it non-autonomous. In this scenario we call it autonomous. Depending on whether we have also, there's going to be a whole bunch of other terminology I'm about to throw at you, but we can talk about when these are constant coefficients. And then when we get higher order ones, there will be more of these guys. There will be ABCs that are all constant coefficients or non-constant coefficients. And then classically, this one will be whether it's homogeneous or non-homogeneous. So first of all, regardless of whether the equation is autonomous or non-autonomous, whether we have t involved or not, we have basically two scenarios, what we're going to call relating xt to xt minus 1 and t. This function can be specifically either linear or nonlinear. So on top of all of the other things that we've had and all the other categories of what a difference equation is, we have one more, which is whether the function is linear or nonlinear. What does linear mean? It's the same as any other context in math. Basically, this difference equation is linear if each term is either a function of time multiplied by one of the unknowns, in this case the xt's, or the other terms could be possibly just functions of time alone. If you have that scenario, that's what we call linear. Anything else is nonlinear. This is going to be the most general form of linear, and we're going to get a way of systematically solving this equation. You're going to get a horrible formula for it, but we'll go along the way, and we're going to break this into 4 categories. If a, first of all, is a constant, then we're going to call that constant coefficient. And then if f of t is 0, we're going to have, I'm going to write them down in a second, but before we start, starting from this is the most general form of linear first order. If a is just a real number, we're going to call that constant coefficient. If f is 0, we're going to call that constant coefficient homogeneous. If it's not 0, then we'll call it constant coefficient non-homogeneous. And then if we allow the a to be a function of time as well, we're going to call that non-constant coefficient. And then if this is 0, we'll call it non-constant coefficient homogeneous. And then the most general form of a linear first order difference equation is non-constant coefficient non-homogeneous. And we do have a systematic way of getting an explicit closed form formula using products and sums of xt from this non-constant coefficient non-homogeneous first order difference equation. The other thing I was going to point out is if this is constant, then being homogeneous and autonomous are the same thing, because autonomous by definition means there's no time involved. But if both of these have time involved, you have to be careful. But if this is now a constant, the only way that you would have time involved is if you would have this function, and the only way you call it non-homogeneous is if you have this function. So if this is a constant coefficient, which is primarily what most people use anyways, and they don't really talk about this one in general, I'm going to do a few of these. But if this is constant coefficient, being autonomous is the same as being homogeneous, but they're not the same in general. All right, here's a demographic of the linear difference equations we're going to discuss and systematically give solutions to. First of all, we have number 1 is constant coefficient and homogeneous, so there's no f. The f of t is 0. This one's going to be first order constant coefficient homogeneous, and therefore this is the only case where we have purely autonomous, no t is involved in that. So if you have a linear first order autonomous equation, it has to look like that, essentially. Technically speaking, that's not entirely correct. If there was a plus b, it would still be no time involved, but then it would be non-homogeneous. The next one that we're going to have is x of t is a xt minus 1 plus f of t. This is first order. As always, I'm just going to drill it into your head because first order means there's only one of these guys. There's no more of them. This is going to be first order constant coefficient. That's still a real number, but now this guy is not 0, so this will be non-homogeneous, and this is of course non-autonomous now because we have functions of time, unless that's a constant function, but either way. Number 3, we now may have where a standing in front of xt minus 1 is actually a function of time as well. This is going to be first order non-constant coefficient and then homogeneous, because at first we will study, we'll add, this will be awfully close to the scenario of how we solve these two guys, and then when we add the non-homogeneous part, we'll show how to solve these guys. The last category is a is a function of time, and we have f of t is non-zero, so this is going to be first order non-constant coefficient, non-homogeneous, and therefore non-autonomous. This is the most general first order linear difference equation, and then of course there will be one more fifth category. What's the fifth category? Non-linear difference equations. So these ones at least we can break into categories and have a bunch of fancy names and terminology for them, but even for the most general one, and why do we break them into these categories? To distinguish between them and to have certain different techniques for solving them specifically. Therefore, the end goal is to have a most general form for the general solution of the most general linear non-autonomous equation, and luckily for linear, we do have this. For nonlinear, all bets are off. Let's get at the specific general solutions to these categories. First of all, definition. By solving a difference equation, this guy, what do we mean by solve it? We mean find a closed form. X of t is some other function of time explicitly for every time t greater than t naught, some starting point. Usually we're going to use 0 and 1 in most cases, but just in case it could be any starting point. And we want it to satisfy the relation. What that means is, right here, we have xt. To calculate this value, we need to know the previous value. So if we actually want to calculate x 100 or 1000, have you ever counted 1,000 things? We're getting ready to do 1,000 integrals, and oh my goodness, compiling 1,000 things is a lot. So if you want to count, so yeah, if we want to actually calculate x 1000, I don't want to list out x0, then x1, then x2, from x1 and then x3 from x2 all the way up to x 1000. I don't want to do that. So what we want is to solve it. We mean find some clever closed form for this guy for every t, and then we can, if we want to know what x 1000 is, we just put 1000 into that function, make one horrible calculation. I didn't say that'd be nice, but it'll be one of them instead of 1,000 of them, and then we can compute at any timestamp we want. For an example to see how we do that, and then where we get, I won't prove it, but essentially the idea right here, the clever trick will be essentially how we can prove a couple of these first theorems. Let's solve this first order constant coefficient non-homogeneous difference equation. This is the number of moves in the Tower of Hanoi game. You start off with how many moves does it take to move one ring to the other peg? One move. So x1 is 1. And then the number of moves, it turns out you have to move 3 rings, then move the 4th ring, then move the 3 rings back on top of it. So it turns out to do the general Tower of Hanoi moves, it takes this many moves in the previous one. So the 3-ring move, then move the 1 ring, and then do the 3 rings again. So then that's how we get this recurrence relation for the Tower of Hanoi, or this difference equation. What do we mean to solve it? We seek some clever closed form for this. How we're going to do this is what we're going to call iterations of the recursive definition or the recursive relation. What do we mean by that? These two are related, but then that means also that xt minus 1 and xt minus 2 are related to each other. Eventually, through these iterations, we want to relate xt to x1, and then all of these guys intermediately are gone, and we have a function of time explicitly, and we can calculate for any time t. Let's do that. So xt is going to be by our recursive relation or our difference equation, this depends on xt minus 1 plus 1. But I know something about this one. I cleverly write this is 2 times xt minus 1 is 2 times xt minus 2 plus 1 plus 1. What does that give me? That gives me, simplifying, I get 2 squared. You'll see why writing 4 doesn't help me see a pattern. Leaving it as 2 squared lets me see the pattern. This is going to be xt minus 2 plus, distribute the 2 in there, 2 plus 1. So I'm already starting to see a pattern, and I've seen how this goes before, so I'm already going to point out what I'm trying to see. I already see it, but I just did this beforehand, so that it helps a little bit. I'm now relating xt to xt minus 2. And when I do that in the formula, I see that I get, when I'm relating xt minus 2, I get it's multiplied by 2 squared. The 2 here matches this 2. And in this, I'm going to see that that's actually the 1 is a 2 minus 1. And then I see a pattern, I think. I'm going to do it one more time. If you can't see it, you just keep iterating until you see this. For the third one, xt minus 2 is related to xt minus 3. How? This will be 2 squared times xt minus 2 is actually 2 times xt minus 3 plus 1 plus 2 plus 1. Distribute that in there again, and I'm going to get, this is 2 cubed this time, times x to the t minus 3 plus 2, don't forget we're going to put it on there, 2 squared plus 2 plus 1. And then what I want to see specifically is, this is what I'm trying to see. Those 3 guys. Where does the sum end? Where's the index? And what's the power of 2? This was a 3 and a 3 and a 2 is 3 minus 1. And that's what I want to see. Now I think I have a pattern. And now what I'm trying to say to myself is I want to relate ... they say. After iterating this to get down to this one, we want to have 2 to the something times x1 plus some sum all the way down to plus ... plus 2 times 1. This, but where do I end? Well, how do I get x1, the index 1? It's, in this one, it was t minus 2, and then t minus 3, and then what t minus what gives me 1? That's going to be t minus 1. The t's will cancel, and I get positive 1. So the index 1 is going to be x, actually t minus 1. And so what do I put in front of this guy? 2 to the t minus 1. And then t minus 1 minus 1 is t minus 2. Now we're almost done, and we'll clean this up a little bit. What is this thing specifically? This is equal to x1 is 1 now. The whole point is we now have 2 to the t minus 1 plus 2 to the, plus 2 to the t minus 2 plus all the way down ... 2 squared plus 2 plus 1. Now we can go one further, and we're going to clean that up and give an explicit formula for what this guy is, and then we have xt is a function of time. Let's do that. All right, moving that up, we saw that by iteratively using the recursive definition, we get that xt is the sum of powers of 2 up to t minus 1 starting at 0. 2 to the 0, 2 to the 1, 2 squared, all the way up to 2 to the t minus 1. I want a nice closed form for this sum though. These general definitions are all going to have a product and then a sum of a product, so get used to trying to get a nice closed form for these solutions. You're going to have to learn all the clever formulas for sums. What is this one? The clever idea is what we're going to do is call this sum s. Let s equal 1 plus 2 plus ... plus 2 to the t minus 1. And then what was my base? My base is 2. So what if I multiply by 2? It shifts all the powers. It'll be 2 times this sum. So and then I distribute it in there. What's that going to give me? That's going to give me no 1s anymore. It's going to shift that to 2 plus ... plus 2 to the t minus 1 plus 2 to the t. Oh, now do you see what I'm going to do? Now I'm going to subtract. I'm going to get 2 minus 1, technically s. And in general, when the base is in the 2 and it's a 3, it has to be like this. So I'm going to get that guy, which is going to equal what? This is going to be a minus, and this is going to be positive, so I'm going to get 2 to the t minus 1. And that tells me that s is equal to the t minus 1 over 2 minus 1. In this case, that is a 1, so we get 2 to the t minus 1. Therefore, we have that this sum cleverly now is 2 to the t minus 1, and this is our closed form. So our function g of t that we were looking for is 2 to the t minus 1, which happens to be Mersenne numbers. If this is prime, this is what's called a Mersenne prime, after Marin or Marin-Mersenne. This is the idea of what we mean by solve a recurrence relation or solve a difference equation. To solve this, we want a nice closed form. So now if I want to know what x12 is going to be, it's 10, 24, 20, 48, 40, 96. So 40, 96 minus 1, 40, 95. This gives us an extremely quick way of computing x12. If I use the original definition, I would have to compute x2, then x3, all the way up to x11, and then use x11 to compute x12, which would be 4095. Let's do a theorem about constant coefficient non-homogeneous difference equations. Read my mind, you son of a... Theorem. For the first order difference equations, first of all, a and b are going to be real numbers if they don't have the of t in there. So first order difference equations, x of t equals some function of just the previous timestamp and possibly the variable t, and we're going to start at some starting point. A lot of them will put x to the, on top of confusing everything else, an index on an index, xt0, so some fixing starting point without loss of generality, or for most cases I'm going to use 0. 0 is where you don't start the process or the experiment, the amount of bacteria after we don't run anything, and then 1, and then you'll get the data from there. So 0 is usually the starting point, how much bacteria there was at the start, and then t equals 1 is the first measurement, and then so on from there. So usually we're going to start at 0. But using that for simplicity, so I didn't have to have the t0 in there everywhere, we are going to just call that a real number alpha for first order, because I only need one parameter for first order. Second order, I'm going to need an alpha and a beta. Anyways, we're going to let x0 equal alpha be our starting point, and then the following closed form general solutions for each of these scenarios is given by these hot messes. Let's go through them one at a time. If we have first order constant coefficient homogeneous, so there's no f, this is the geometric sequence. In classic grade school, you do geometric sequences and their solutions, and arithmetic sequences. Arithmetic are right here, these ones. What is the geometric sequence? If you have this where it's constant coefficient, so it's just a number, and then no f term, the general solution is a to the t times your starting point. This is the one we did in our example previous. This is the Tower of Hanoi one. A was 2 and b was 1. If you have this, this is constant coefficient and non-homogeneous. What that gives us is, if a, we're going to get into this in the next chapter when we do higher order, we'll actually talk about other theorems which do look at this in a slightly different manner, but we're going to get a characteristic equation from this, and if 1 is a root of that characteristic equation, then it ruins everything in there. So why did this break into 2 cases? For now, because I said so, but I'll explain this a little bit better in the sections to come. So if we have x of t is a xt minus 1 plus b, the general solution is, if a is not 1, also for the justification right now, we're dividing by a minus 1. So if a is 1, we can't do that, and we can't use the clever trick that we just did for the Tower of Hanoi iterated substitution, because we won't be able to divide by a minus 1 at the end. When we did as minus s, when we divide by 2 minus 1, it was just the number 1, it was okay. But if we have a is specifically 1, we'd be dividing by 0, and we know we don't want to be hit by lightning, so we're never going to do that. If we actually have a as 1, this actually becomes a much easier thing to solve. Try it for yourself, and then I'll give the proof one of these days in one of the videos, but the general solution is this guy. This is arithmetic sequences. So this is geometric sequences and their solution, and arithmetic sequences and their solution. Specifically, arithmetic is when you have this guy, a common difference, and then you just keep adding that, or you keep adding the same multiple. So, having said that, getting almost to Papa Bear ones. The Mama Bear one is, it was still homogeneous now, there's no f term, but A now is not constant, it may be a function of time itself. When we have that, now using the same actually clever trick, what we did was we just iterate and put xt minus 1 is a times xt minus 2, and then you'll have a squared, and then you get it all the way down. What we're going to do is, it doesn't matter if there's a of t in there now, but what you're going to get is what this product guy says is, what is this product? The product, let's try one, from I equals 0 to 3 of ai. What does that actually mean? That says you start at 0, so you're going to have a of 0 and compute some number. Then you're going to start running it, and it's going to be multiplied instead of added. And then it's going to be a of 1 times a of 2 times a of 3, all multiplied together on one row, but I ran out of real estate. So that's what this product symbol means, and this is the general solution for this non-constant coefficient but homogeneous first order difference equation. For the final one and the most general scenario for a non-constant coefficient, non-homogeneous first order difference equation, which is linear, this is the most general form, and luckily we have a meme already. I know it's a hot mess, but what would you have done without this hot mess? Hands to the air, I guess, but at first, and then you try to regroup, and using a technique similar to this, but then you have this extra term in there, be careful, you're going to get that the general solution is, again, this product, just like this term, but then you're going to get an extra sum of a product of a what the heck is going on here. Let's do an example, and then we'll finish this video. All right, example 2, use the theorem that we just discussed to find the general solution of each of these first order difference equations. For the first one, it's the Tower of Hanoi. Now we're going to try and use the big machinery. When you get this big machinery, hopefully it calculates the same solution as you had when you didn't use the big machinery. For the first one, what we're going to get is, first of all, let me put that horrible formula for the most general case and see if I can spit it out. xt is going to be, for the general, a of t xt minus 1 plus f of t. The most general form for that guy is going to be the product from, technically, let's do I equals t naught, the starting point, to t minus 1 of ai, all times alpha, the starting point, plus the other term is going to be now the sum from r equals t naught. In general, that is going to be a 0 or 1. I've given a 0 and a 1, so we'll see what to do with that general formula, to t minus 1 of the product from I equals r plus 1 to t minus 1 ai, all times f of r. Ugh, that's horrible. Now, I'm trying to use that in both of these scenarios. You can use the categories, but really what you want to memorize is the fourth statement, because that's the most general solution to these first order difference equations. Now that we have this in mind, what we're going to do with this guy is try to specifically, for all of these details, this is going to be my a and this is going to be my f, this is going to be my a of t, and this is going to be my f of t. We're going to try and see and get a clever formula using this hot mess. Or hands to the air and give up, I guess, but those are our only two options, so I'm going to use this guy. What do we get with that specifically? I now know that, first of all, my t naught is 1, this guy, and this guy. Then what else do I need in here? My a, who is that guy? In this case, we have constant coefficients, so my a of t is just a 2. This is a real number. And then what is my f of r? My f of r is a 1. So my f of t is 1. And my starting point alpha is also 1. With this information now, that's the first thing you want to do, is solidify those 4 things in your mind, what those pieces are. What's my starting point? What is my initial value of that starting point? Then what is the a of t and what is the f of t? Once I have those, I have to put those into the product formula, and I'm hoping that I get 2 to the t minus 1, the same thing we got the first time. Once I have these guys, that tells me that xt is going to be, using this hot mess, we're going to get, my t0 is 1, so we're going to get, for the first term here, I'm going to get the product from I equals 1 to t minus 1 of my function is just a 2 times alpha, which is also 1, but I'll leave it for now, and we'll do it in the next step, plus, now in the second term, I'm going to get r is t naught is 1 again, so we're going to get the sum from r equals 1 to t minus 1 of, now in this one, we're going to get a product from I equals r plus 1 of t minus 1 of ai, which in our case is again a 2, and then multiplied by f of r. F is just a constant function 1, so that won't change. You'll see it when they get more complicated, it does change, it's worse, but right now that's just going to be a 1er every time. What does that give me? Well, now for this guy, this one, first of all, this is equal to, this guy is what? 2 multiplied by itself, t minus 1 times, so that is 2 to the t minus 1 times 1, because alpha is a 1. For this term, when r equals 1, the first term of this horrible symbol is going to be, the first term is going to be some product multiplied by 1. So what is that product? It will be when r is 1, I is going to be 2, so it's going to be the product from I equals 2 to t minus 1 of 2, which is going to be 2 to the t minus 2. When r is 2, for instance, and then I want to stop eventually, when r is 2 now, what's going to happen? If the next term is going to be some product. The next term is going to be what? This will give me I is 2 plus 1, so 3, so it will be the product of I equals 3 to t minus 1. We're losing one of the 2's every time of 2, which is going to be 2 to the t minus 3. And then dot, 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 when we put that last guy in there, what am I going to get? The first term was 2 to the t minus 2. The next term was plus 2 to the t minus 3, plus all the way down to plus 2 squared plus 2 plus 1. And we saw last time that this is 2 to the n, or sorry, n. I'm so used to using n. It's time now. 2 to the t minus 1 over 2 minus 1, which is in fact 2 to the t minus 1. This gives us, even though, yes, at first we want to scream at the air and quit and throw everything, I'm done with this. No. Once we back it up and we analyze a little bit more and we meditate on this theorem, it does give us exactly what we wanted. Let's do one where we have now non-constant coefficients and non-homogeneous, the most general form of linear. Then we'll let you bask on the plateau of, I know how to solve them all, and then I'll point out non-linear, higher order, systems of equations, continuous, what's going on? To finish off, we're going to solve this hot mess. It's the most general form of first order difference equation. It is both non-constant coefficient and non-homogeneous. We're going to use this clever formula, or hot mess, or nightmare, depending on your viewpoint, or savior, to give the explicit closed form solution, general solution to this first order recurrence relation, or difference equation. How do we do that? In this one, we're going to do the same thing we did for this simpler scenario. We're going to define what everything is. First of all, in here, I need to know what T naught is. T naught is going to be 0 in this case. That's my starting point. We also know that alpha is going to be 1 again. The other two things I need are my A and my F. Now we see that A of T is T plus 1, and our F of T is 2 to the T plus 1 factorial. The first thing we should notice is, and I've done this before, specifically just before this actually, I know that what is A of I and F of R, so you should remind yourself of that. A of I is going to be I plus 1 when we specifically use the formula, and F of R in this case is going to be 2 to the R plus 1 factorial. And as I've set that up, I have the 4 things I needed in green, these 2 guys and these 2 guys. Now I'm going to use this hot mess. What do I do with that? This gives me x of t is equal to a product from I equals my starting point 0 to t minus 1 always of ai. In that case, ai is I plus 1 multiplied by alpha, my starting point, plus a sum now, always to t minus 1 of r equals my starting point, 0 in this case, of a product times my non-homogeneous part. This is going to give me the product. It's going to go from I equals r plus 1 to t minus 1 of ai, which is again I plus 1. That's multiplied by f of r, which is that guy. Oh, 2 to the r plus 1 factorial. Leave it. No, now you have to clean it up, unfortunately. What I am going to do is erase this because I don't need it anymore. I think I got it right. We'll see if I got it right. How will you know if you got it right? I'll tell you, I guess. Now what do we get? Let's simplify this out. This is a 1, first of all. So this is equal to the product. Put I equals 0 in there. What do I get? I'm going to get 1 times. Put I equals 1 in there. I'm going to get 1 plus 1 is 2 times. Put I equals 2 in there. I'm going to get 2 plus 1 is 3 multiplied by all the way to, what do we get? We stop at t minus 1 plus 1. That is all multiplied by alpha, which was a 1. That term's done. Hopefully you can see that these are going to cancel. And this is a t. So this is 1 times 2 times 3 all the way up to t. That's t factorial. This one, we'll do that in the next line. This one is now going to be the sum from r equals 0 to t minus 1 of, what is this hot mess now? First of all, let's rewrite this one in the front to the r plus 1 factorial. That guy is r plus 1 times r times all the way down to 3 times 2 times 1. And now what is this thing? This is starting at r plus 1. When I is r plus 1, that's r plus 1, which is r plus 2. What? So the first number in that product is r plus 2. Then going on from there, we're going to get, where are we going to stop? We're going to stop at t minus 1 plus 1, which is t. What is that? Now this thing is t times t minus 1 all the way down to r plus 2 times r plus 1 times all the way down to 3 times 2 times 1, which is also, again, t factorial. Therefore, what this gives me is, this one is t factorial, and this is plus t factorial times the sum from r equals 0 to t minus 1 of 2 to the r. What is that? Again, using the formula, this is t factorial plus t factorial times, what are we going to get? 2 to the t minus 1 over 2 minus 1, which is equal to, what do I get? T factorial plus t factorial 2 to the t minus, this is a 1 on the denominator, which is t factorial. So these cancel, and I get t factorial times 2 to the t. A nice closed form. Let's move that up and give the general formula or general solution to this non-constant coefficient, non-homogeneous, first order linear difference equation. I think that was all of them. All right, so this first order linear non-constant coefficient, non-homogeneous difference equation, I always want to call it a recurrence relation, but they're the same thing essentially, has general solution or closed form general solution of xt is 2 to the t times t factorial for every t. What that means is, if I want to know what x4 is, for instance, if I don't know what the solution is, picture 4 being 4,000 for some ridiculously large number that I don't actually want to calculate, but even for 4 here, what I would have to do from starting with x0 to get x1, if I don't have this clever form and you pretend we don't know what it is, or you're like, I already forgot what it was anyways, what was it? 2 to the t times t factorial. But if I don't know that, to calculate t1, or to calculate x1, I would have to do this formula. So it would have to be 1 plus 1 times x0 plus 2 to the 1 times 1 plus 1 factorial, and then compute that. And then I'd have to compute x2 is going to be 2 plus 1 times x1 plus 2 to the 2 times 3 factorial. And then I have to compute this, and then I have to compute x3, and then I have to compute x4. Or we can do x4 is going to be 2 to the 4 times 4 factorial. She wanted to see how to do the end calculation. I know, just like everyone else doesn't want to see the whole video. They just want to be like, how did you calculate at the end? Okay, here we go. To calculate x4 is going to be 2 to the 4 times 4 factorial, which is going to be 16 times 24. Oh, now we have to do arithmetic. Oh, I'm going to put the 16 on the bottom. That'll make it easier for me to calculate in a second. So I'm going to get 24 I'm going to get 4, and I'm going to get 0, 4, 2, I'm going to get 4, 8, 3. So we get 384. I know it's still not easy and it's non-trivial, but I immediately, in one calculation, get the value of x4 instead of having to compute the iterated thing. Now think about having to compute x 2020. At least I know that it's 2 to the 2020 times 2020 factorial, which is some horribly ungodly large number, but at least we have to make one horrible calculation and not all of them all the way up to 2020, right? All right, she doesn't know anything. Please subscribe right here. I'll see you next time. Kitty drop. No, don't drop the kitty.